Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. This is for my integrated math 2 classes who are in their geometry units. In this current geometry unit, we're looking at some polygon things. We saw the polygon angle sum theorem, and then we're digging into some triangles. Remote exterior angle theorem, triangle inequality theorem, isosceles and equilateral triangles. This week we're going to dive into quadrilaterals, so a bunch of different polygon shapes. And so for the last couple weeks, they submitted some questions. It looks like 6 questions only. Only 6 questions. It should be relatively short unless I decide to, I haven't looked at the questions yet, so unless I decide to spend a long time going over them. For the last 2 weeks, they asked some questions for me in which I will attempt to answer for them. They should be content-based and relevant, but they should not be so specific that I'm just answering that one individual item like, can you do this from this homework or something. So anyway, I give them credit for it, and then afterwards they follow up and respond to some of the questions, especially if they ask them, then they get a little more credit for it. So I'm going to go ahead and get started here, guys. Like I said, only 6 questions. Let's see how fast this thing can go. Question number 1. Why is one inequality proof always negative? Referring to triangle side inequalities. Proof. I really should look at these questions before. What I think's being, because I see the word negative, what I think is being asked is, when using the triangle inequality theorem and trying to find out the range of a certain side length, why is when testing all 3 times, it's kind of a longer question this way, why is when doing all 3 tests on the theorem, one of the results always negative? Actually, part of the answer is it wouldn't always be negative, but we haven't seen one of those. Let's go ahead and take a look at kind of what you're asking, and we need to break it down in kind of a bigger way. It's a good time for me to teach the triangle inequality theorem, or reteach it as well. So the triangle inequality theorem states that if you, in order to properly build a triangle, the sum of the lengths of 2 of your sides always must be greater than any third side. So if I add A and B together, it must be greater than C. If I add B and C together, it must be greater than A. And if I add A and C together, it must be greater than B. If one of these is not satisfied, then a triangle is impossible to build in that scenario. So for one example, and I promise I'm going to answer the question based on this, but for one scenario here, let's say we had side lengths 5, 7, and 10. You know, if I do these tests, is 5 plus 7 greater than 10? Is 7 plus 10 greater than 5? And is 5 plus 10 greater than 7? The answer is yes to all 3. Therefore, this is possible to make a triangle with those side lengths. Otherwise, it gets too short, right? If it was 5, 7, and 15, then 5 plus 7 is greater than 15. 5 and 7 can't reach to kind of make the triangle, if that makes sense. But anyway, so there are 3 different tests that we can do. I mean, as per the theorem, 3 different tests. But you'll notice that only one test is really even worth doing, because 2 of the tests kind of show one side length that is larger than the other end. When we do 5 plus 7, checking to see it's greater than 10, this one makes sense to do because 5 and 7 themselves individually are not more than 10, but added are they more than 10 is the test. When we do these ones, 10 is already greater than 5. There's no value in needing to add to check and see if a longer side added with some other side is greater than a side shorter than 10 is already greater than 7 here. Heck, 7 was already greater than 5 here. So these 2 aren't really worth doing when you know all 3 sides here. Right? You only take the 2 shorter sides and compare it to the longest side there. So the question that's being asked, and so let me revise this now. The question being asked is, why when we're doing the tests, this all got grouped as one, hang on. Why is it when we're doing the test here against not 3 known sides, but 2 known sides, and then an unknown side here? Let's look at these 3 again. X plus 5 greater than 10. 5 plus 10 greater than x, and x plus 10 greater than 5. If I tested these and solved for x in all 3 inequalities, here I'll get x is greater than 5, here I'll get 15 is greater than x, and here I'll get x is greater than negative 5. They're asking, why is one of these always negative? Why is one of these always negative? And the answer is, as we looked back at the previous example that I kind of gave, you're testing a side that is known to be longer than one of your other known sides that is shorter, and we're assuming this is the longest side here. See, when we look at these 2 examples right here, it's a test worth doing because we don't know if x is one of the 2 shorter sides or the longest side potentially. If x is the longest side, we need to take that into account. 5 and 10 could be the shorter sides. X could be side length 13 maybe. As long as it's less than 15, it's valid. And x could be one of the two shorter sides here. Apparently, it needs to at least be greater than 5 to still work out here. Maybe it can't be the shortest side, but it needs to be one of the shorter sides because we don't know how long x is. Here, you might say, we don't know how long x is here either. Yeah, but we know how long 10 is, and we know how long 5 is. There's no reason to make a test with this because no matter what you put in for x, assuming distance is positive, no matter what you put in for x, this will always be greater than 5. This is not a valid way to figure out what x needs to be here because 10 is already longer than 5 in and of itself. The same reason why we don't need to do the two other tests on those other two instances where 10 or whichever numbers were longer than 7 or 5 when adding and checking it. But the difference here is we don't know how long x is, and it could be one of the two shorter sides or the longest side, and then just make sure that the other two on the left side are shorter than are known to be shorter than anything known to be longer. 5 is definitely shorter than 10. 10 is definitely longer than 5. And so hopefully that kind of answers that question there. Now the other part that I want to mention is you said why is 1 always negative? They might not always be negative. What if I do this? What if I made an at least isosceles triangle here? What if I made this one 5 as well? So now we're going to check what? X plus 5 is greater than 5. 5 plus 5 is greater than x, or the third one doesn't really kind of... It's going to be the same thing as this, right? Swap the 5s. So there are only two tests here as well. If I do this one, this becomes x is greater than 0. And here this is x is... 10 is greater than x or x is less than 10. So as long as x is between 0 and 10, it's there. There is no negative instance in that one because two sides were the same length here. Anyway, as long as x is a number between 0 and 10, you'll make a triangle. You will make a triangle there. It's an isosceles triangle, I guess, or equilateral if x is 5, which is valid. All right, there is that question. I hope that I answered it in great detail. I hope that that did make sense. Let's go on to the next question here. Can you please do a problem by using the triangle inequality theorem? I technically just did one. So I will have you kind of go back and check that out. But we did not see one where it does not get satisfied. So I'll go ahead and do that for you right now. We just looked at one that had 5, 7, and 10. So 5, 7, 10. Using that, we checked to see if that worked out. Let's try something. I gave another example kind of out loud, 5, 7, and 15. Using this, we want to see if we can actually make... Now, by the way, they won't always draw a triangle out here. In fact, this shouldn't be a triangle because 5 plus 7, the two shorter sides, is it greater than 15? Well, 5 plus 7 is 12. 12 is not greater than 15. Therefore, this will not give you a triangle. That's just testing it using the theorem itself to see if these three sides do it. Now, again, the reason behind this is 15 is just so long that if this is length 5... and this is length 7, and not drawn to scale clearly, they just don't reach to connect. They're not close enough to connect to one another to make a triangle. And as you saw, it needs to be greater than 15. Even if this was 10, guys, even if this was 10, the only way that these two connect, the 5 and the 10, is if we flatten them out completely. That we flatten this out right here. Here's your 5, and here's your 10, and they connect right there, because 5 plus 10 is 15. But that's not a triangle. It needs to be at least a little bit longer. Even if it's 10.1, at least now 5 can go a little up, 10.1 can go a little up, and it'll make a triangle, right? It needs to be greater. Just keep that in mind. But that's the theorem in and of itself when you test three known side lengths, and I just kind of showed something where one of the side lengths is unknown, and when you test its range. So there it is. I hope that kind of made sense. And there's question number 2 down. Question number 3. If you know the length of one of the legs of an isosceles triangle, can you determine its... Excuse me. Let me read that again. I can't read right now. If you know the length... I think this was a homework question. If you know the length of one of the legs of an isosceles triangle, can you determine its perimeter? If you can you show us how? Also, second question. Make sure you submit... Guys, make sure when you submit in this thing, you do different questions. Submit the form... Submit 2 different... Go back to the form, submit a question. I can't talk right now. I'm sorry. Submit your first question, then go back to the form, submit a second question. Okay, because this is harder for me to break apart. Sometimes I accidentally skip one of your questions when you do this. Okay. Also, I was wondering if you could do problem 16. I asked you guys not to do this. Problem 16 on page 749. My tutor was really confused, and so was I. Thanks. Now, keep this in mind just before I answer either. First of all, these are both homework questions. The first one is a homework question. The main reasons, and this isn't particularly true for you guys because I didn't make a solution guide video, but the main reasons why I don't want you to ask specific questions like these, the first one's not specific, but it is a homework question, is because if it is a homework question, generally I would do it in a solution guide video. or I do it in class, or it's something you can see me for in tutoring. And also, it gets very, again, the first one isn't, but the second one is probably a very specific question that only covers that question alone. It doesn't cover an umbrella set where I can kind of talk around it. Sometimes I can, but sometimes they ask you something that's too restrained, and I can't really dance around that thing. So try and avoid doing this here on out. I don't know if I'll give you full credit even for asking 2 questions for these things, because even though the first one's pretty good, it was also a homework question. I'd love for you to ask during class or during tutoring if you could. But let's go ahead and answer them. First one, if you know the length of one of the legs of an isosceles triangle, can you determine its perimeter? So again, if this were a question on its own, it would actually be a pretty good one, meaning if it wasn't in homework. So an isosceles triangle, guys, looks like this. 2 congruent sides, 2 known congruent sides right here, and those are called legs. So these 2 sides right here, this is a leg, this is a leg. This is technically called the base. It is not known to be congruent. We can't assume it to be congruent right there. By the way, 2 congruent angles here called base angles. Base, angle, base, angle. So each part in this triangle has a name. This part up here is called the vertex angle. Anyway, the reason I bring all that up is because they mentioned the word leg. If you know the length of one of the legs of an isosceles triangle, can you determine its perimeter? Well, that's a good question. What if, let's erase some of the names here. What if I gave you that a leg length is 10? Okay, get its perimeter. Now, perimeter means adding all 3 sides and getting that entire length. If this is 10, then we know this is 10, right? But what's this? It's not known to be 10. We can't assume that it's 10. We know that it has to be between what numbers? 0 and 20, right? Triangle Inequality Theorem. I kind of just brought that up in, I forget if it was the first or second question, but I think the first question. But yeah, the third length has to be either, it has to be more than 0 and it has to be less than 20, because 10 plus 10 has to be greater than your third side. But that's the thing. This thing can vary. It can be any length between 0 and 20. So I can give you a range of what the perimeter can be. It has to be more than 20 and less than 40, I think. Because think about this isosceles triangle here with lengths 10. I could make these side lengths 10 and 10 like this, right? Let's say this was my 10 and 10. So this is 10 and 10, and this is, I don't know, 1. You know, pretend like it's that. And alternatively, I could make, I should delete this. Alternatively, I could make another one that's 10 and 10 like this, right? What if this is my 10 and 10? And then that third side is super long, 9 or something like that, right? So we don't know what the third thing is there. So no, you can't do it just by knowing one of the legs. You'd have to know more information. And some of the other things are, you probably wouldn't know how to do it now, but down the line you might learn if you knew one of your angle measures, it would actually be possible using trigonometry. If you knew, I don't know, that's it. If it was an equilateral triangle, yes, you would know. They wouldn't be called legs anymore, by the way. They would all be 10. You know, equilateral or equiangular. But no, it's impossible to know the perimeter just by knowing one of the legs. You'd have to know the base length as well, or some other bit of information. Okay. I almost skipped your second question. All right. I'll give you another reason why I don't like you asking questions like this, because I don't know what you're talking about, and now I have to go look for it. But can you show, I was wondering if you could do problem 16 on page 749. So now I have to go look for it, and I wasn't prepared for that. Maybe you can say, well, that's your fault. You should have been prepared. No, this isn't, that's not how I do my power hour video. Sorry. So I'm going to go look for it. Give me a second, because I don't even know what assignment this is from. I don't know. I'm not going to dig up page 749. I'm going to find it on our homework here. So, problem 16. I'll tell you, I know problem 16 was on section 50. See, I don't know. 15. I have to look for it. Oh, here we go. Page 746, 749. Okay. So out of here, actually, you know what? Let me kind of copy and paste it in. So, sorry, this is taking up time. You know what? Let me pause the video and go find it. Okay, here is the problem. Number 16 on page 749. John is building a doggo house. Doggo. He decides to use the roof truss design shown if measure of angle DBF equals 35 degrees. What is the measure of the vertex angle of the isosceles triangle? Okay, so in this problem here, here's the isosceles triangle ABC. You can tell by the marked side lengths here, which means we know for sure this is isosceles right there. Congruent sides also means congruent base angles right there. And they have a 2x plus 15. Oh, one thing about this problem that I found out when doing this problem with other groups is You don't need this. I don't know if this was meant as decoy. Unless they ask you to solve for x here, the 2x, you don't need this expression, actually. It's kind of interesting. And I'm trying to think of a nice way to use the 2x plus 15 to actually assist me in the problem, and it's really just not worth it. You're going to try and find one of the angle measures anyway. The other part of this, guys, is the vertex angle right here. Vertex angle is this top part. So this is what we're trying to find. We're trying to find the measure of angle BAC. Okay, if measure of angle DBF is 35 degrees, now this DBF is right here, that's 35. It's always good to mark this thing up. And by the way, a right angle is 90 degrees. That's also helpful. Now, the way that I want to go about this problem is if I can find out one of the base angle measures here, then I'll know what the other base angle measure is, and then all three of these will add to 180, and then I'll just solve for A. So, all that being said, guys, I have, it's not a linear pair, but a linear trio. Measure of angle DBF, the right angle, and measure of angle ABC right here, all add up to 180 because they're adjacent and form to make a straight angle. So what I'm just going to do here, guys, I'll take the 35, and there might or must be another way that they wanted me to do this. I'm just not going to pay attention to that. But 35 plus 90 plus some unknown, let me call it x, this thing right here, or measure of angle ABC, equals 180. All three of these they are a linear trio, and they add to 180. So 35 plus 90 is 125. X plus 125 is 180. Subtract 125. I'll get x equals 55. 55 degrees for the measure of that angle. So if this one right here is 55 degrees, well, then that means that this one up here is also 55 degrees. You can tell I'm really not using this at all. I don't really know, again, unless they say solve for x, which they don't, then it's not needed. These two 55s plus this unknown, I'm going to call it measure of angle BAC, add to equal 180 as well, because it's the interior angle sum of every triangle. So 2 55s plus the measure of angle BAC equals 180 degrees, and then that's 110 plus measure of angle BAC is 180. Subtract 110 from both sides, measure of angle BAC equals 70 degrees right there. Degree symbol, of course, is important, and that is your final answer. Measure the vertex angle. Definitely not poo-pooing on your tutor here at all, but once again, if you are struggling, definitely visit office hours, tutoring, stuff like that, or ask the question in class, because although I took some time on the power hour thing, I want to try and not do it, because this problem was so specific. Sure, it covered some things. This is a vertex angle, and linear trio adds to 180, and mark the 90. But, again, this was so specific that it only answers one question for one thing. If I do a different kind of problem with a different kind of diagram, what do I do from there? You'll still have the same kind of question, I assume. But hopefully you learned something there, and we can go on. Okay, next question here asks, what is the difference between the equilateral triangle and the equiangular triangle? Well, there's no real difference because every equilateral triangle is equiangular, but equiangular means all angles equal, and equilateral means all sides equal. When you hear lateral, another word, I don't know if another word for lateral is side, but when you think of something laterally in math, in geometry, you're thinking of side lengths. So anyway, equiangular means all angles congruent. Equilateral means all sides congruent. So in a triangle, an equilateral triangle, we will have marked, hang on, I'm trying to find the tool of an actual equilateral. In equilateral triangle, we will mark all side lengths congruent to begin with, or they might mark them all congruent, and therefore we call it equilateral. And then in an equiangular triangle, all angles are marked congruent as such. Now again, every equilateral triangle is equiangular. Every equiangular triangle is also equilateral. Now part of this goes to one of our other talks that we've kind of referred to. Now you see three things marked. Oh, by the way, these are all 60 degrees here. Part of this kind of goes to another talk that we've been bringing up lately on the section of Triangle Inequality Theorem, is that the larger an angle, the larger its opposite side length for a triangle. Right, so opposite this angle will be that side length and this and that. Now, if they're all equal angle lengths, then they're also all equal side lengths. So that seems to measure up that way. So why do we distinguish between equilateral and equiangular if they're both the same thing? Well, that's because triangles are unique in that way, that the larger an angle, larger the opposite side, and if they're same angle, then that means they're same opposite side. But what if you have another shape here where we have, listen, I'm gonna make a, let's do a six-sided shape. I'm going to make a hexagon here, and this hexagon will be equilateral. All right, so 1, 2, 3, 4, 5, 6. You can also it's called a regular hexagon. Now, all of these side lengths congruent might make you think that all the angles are congruent. Now, in this particular drawing, both will be true. But let me give you another scenario here. Let me draw another version of this. I think I have the tools to do this. Let me see if this works. Show hide vertices. Perfect. Now let me give you another version of this where it looks maybe something like this. Here's another equilateral hexagon because all of these are congruent. But are all the angles congruent? Well, these four are. No, these three are. But these ones, maybe these two are congruent to each other right here, but this one is its own convex angle right there. An equilateral hexagon did not necessarily mean an equiangular hexagon. So, there are, and I could probably, I don't know if I could make an equiangular non-equilateral for a hexagon. I'd have to think about that. Maybe, maybe not. But anyway, here's an equilateral that's non-equiangular, right? So for triangles, though, it is locked in place with that. So just kind of something to think about. But anyway, I know that I probably answered your question right from the jump. Just equiangular means equal angles, equilateral means equal sides. But I wanted to include the other stuff because you might also be asking, then why do we, if why, equal angles is equal sides, why do we distinguish? Because there's a little more to it. Okay, next question. How do you know when solving for x if you are supposed to set it up equal to 180 or equal each other and solve? I like that you're trying to get... I know that there are a lot of problems where we solve for x and stuff, but be more specific. I assume we're talking about things with triangles and stuff. I don't know, because listen, we've had isosceles triangles where we set things equal to each other, like the base angles and stuff. The basic premise of your question is, what are the properties of your shape? In this case, in a triangle, if it's an isosceles triangle, what are you trying to achieve? Besides solve for x, what is it that's going on? Here's a tale of two different isosceles triangles, or they could be the same, it doesn't matter, but where you have different labeling in them. In one isosceles triangle, I'm going to give you that this is 55 and this is x. In another isosceles triangle, I'm going to give you that this is 55 and this is x. Okay? Both of these are isosceles here, but, what do you do? And obviously these are very, basic, rudimentary problems. Both of them have different things because it depends on what part of the triangle you're looking at here. In this isosceles triangle, sure, the angles all add to 180. Don't get me wrong, they all add to 180, and they do here too. But I'm not trying to add things to 180 here. I have no known thing for this angle measure right here, and I already know, based on these two things being equal here, that these two angles here are congruent. So 55 equals x. That's my setup. I'm setting them equal to each other. I just solved because there's nothing else to do. But I set them equal to each other because they're equal to each other. That's how I know that. Now, there's something here. These two are not equal to each other, or they're not known to be, because this is the vertex angle, and these are my congruent base angles right here. So now I start to kind of explore this concept of, well, how can I represent this angle knowing that they're congruent? I guess if this is 55, then this is 55. And now I have enough information to say, well, these aren't equal to x on their own, right? There's nothing like that. But I do know that all three angles in a triangle add to 180. So I'm just going to say, well, I have both of my, I think this goes back to one of the problems I had, but 2 times 55 plus x equals 180, and then I would solve from there. I get x equals 70. So, it just depends on the problem and what you're doing with it. The adding to 180 really comes in. How do you know when you should add to 180? When you're referring to the interior angle measures of a triangle, and you're trying to add them up and set them equal to 180, or when you're referring to like a linear pair, or two supplementary angles and adding up equal to 180. By the way, I saw this on a couple quizzes. People were adding side measures to equal 180. What if this was 55 and this was 55 and this was x? They were adding these up to 180. Side measures don't add to 180. That's an angle measures thing. So just be careful on that. I'm not saying that was you. I don't know who this is who was asking it. But I'm just saying be careful. It's an angle measures thing. So when do they add to 180? If you're looking at angle measures, and then if you're talking either about the interior angle sum of a triangle or supplementary angles, right? When you set things equal to each other, when you know they're equal. So if you're talking about an an isosceles triangle and both these sides here are equal, or both these angles here are equal, or an equilateral triangle where all the sides are equal, or, and I don't know if this is one of those cases that you're asking about here, we've been referring to the remote exterior angle theorem, which is where this throws one of the bigger wrinkles for people, because some people don't really know the theorem very well, so they want to use conventional means of adding up to 180, which is fine if you don't make a mistake on it. But let's say that we have a known exterior angle here, which let's call this 120 right here, and then you have x, and then you have, I don't know, 64. So we have these three angles right here, and ask you to solve for x. How do you know whether to add to 180 or to set equal to each other or whatever? Well, there's a theorem in play that says that the two non-adjacent angles with a remote exterior angle are equal. If you add these up, one equals the other. So you can do that, obviously, and then you solve and you get, what, 56? So you can get something like that. But you can also take 180 minus 120 and get 60. Figure out that that one's 60 degrees, and then add these up, set them equal to 180. But again, I know that I add them up and set them equal to 180 because that's three interior angles of a triangle. So I don't know. Just answering the question, it's that you got to know some of the properties of your shape, and you have to know what it is that you're trying to achieve. I'm not going to set x equal to 60 because I have no knowledge that they're equal to each other unless this is known, or they tell you it's isosceles, or if this is known here. So it's all problem dependent, man, or woman, dudette. It's all problem dependent on what you're doing here. Just kind of, have this awareness of what your shape is and what you're doing. Always have an inner dialogue. Obviously, I talk a lot. I'm talking a lot right now. Give yourself the inner dialogue of what is it that I have, and what do I do with it? All right, last question is, what is the meaning / definition of scalene and isosceles? We haven't really dived into scalene much. I mean, here's an example of a scalene triangle right here in the last example I just did. A scalene triangle is, so there are three different kinds of triangles based on angle and side measure compared to one another. There's and I think it's in one of my sets of videos of notes and stuff. So there's a scalene triangle, which basically just means, I don't want to make it look isosceles. There's a scalene triangle, which basically just means that no side lengths are known to, or all side lengths and all angle measures are not congruent to one another. So right here, everything's different, right? Everything's different. Then there's the isosceles triangle, which has two side lengths and angle measures are congruent to one another. So those two. And then there's the equilateral triangle, which says all side lengths and angle measures are congruent to each other. So boom, 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 boom. So three different types of triangles you can get there. And then if you saw my video with the breakdown of those three, there's also a different ways you could define triangles based on the largest angle in it. It can be a right triangle if the largest angle is a right angle. It can be an obtuse triangle if the largest angle is obtuse, more than 180, or it can be an acute triangle if not just the largest angle, if the largest angle is acute, but all the other two are acute as well. So right, obtuse, and acute. And with it, guys, a right triangle could also be isosceles or scalene, so you can have different things like that as well. Obviously, the right or obtuse triangle can't be equilateral because they all have to be 60. That would only be left for the acute. And anyway, I hope that covered it. All right, so that's all 6 questions there. I hope that all made sense. Thank you so much for watching Mr. Robinson's Q&A Power Hour for Integrated Math 2. Take care.